All right, welcome to a segment I like to call Peyamstagram, which is also my Instagram handle, but that's something else. And in fact, I want to show you now that systems of ODEs can give you quite incredible graphs. In fact, this is one of the reasons I fell in love with that subject. In particular, let's consider, for instance, x prime is minus 0.5x plus y, and y prime is sine of x. So nonlinear system. And if you plot it using p-plane, then you get the following beautiful thing. I mean, just look at this thing. I have never seen a more beautiful thing. And in fact, if you're a little bit artistically minded, you may recognize this as a very famous painting called The Starry Night by Van Gogh. I mean, I always figured Van Gogh was kind of a mathematician. And in fact, here you can see this ODE in the middle, which is so nice. And in fact, if you like those two things and you want more, no problem at all. Take the same ODE, but change the x to a 5x. And then you get many things. Oh, so pretty. And people say, I hate math. How can you hate such a beautiful thing? And the next one I really like too, it's called a wishy-washy ODE. X prime is sine of x times sine of y. Y prime is cosine of x times cosine of y. And it looks as follows. Like little things. And especially what I want you to notice, this is like an art gallery, notice the change in orientation here. Because on this one, it goes counterclockwise. Whereas on the adjacent one, it goes clockwise again. So kind of cool here. In fact, here's a nicer picture of what it looks like. The next one, we talked a little bit about it, but it's called the pendulum equation. In fact, it looks like little eyes that are watching you. And the next one is actually my favorite example. And I kid you not, it's the thing that got me hooked to ODEs. So I took that in ODE class and I was like, that's what I want to do. And it's related to what's called the harmonic oscillator, the coupled harmonic oscillator. So consider x double prime is minus 4x, y double prime is minus 4y. And it's a simplified version of the double mass spring equation that we talked about. Now, this system, it's not too hard to solve because there are two decoupled systems. So you can solve them separately to get a cosine 2t plus b sine of 2t, and then a c cosine of 2t plus d sine of 2t. And in this case, the solution is quite nice. It just lies on an ellipse like that. But now the question is, what if we change those numbers a little bit? Then, like for instance, x double prime is minus 4x, y double prime is minus 9y. Then it looks a bit crazier, but not too crazy because, well, it's still a closed curve called a Lissajous figure. And what if we change this 4 to a 25? So x double prime is minus 25x, y double prime is minus 9y. Still okay, still a closed curve. But notice what happened here. If you take 25 over 9 and take the square root, it's still a rational number. And the question is, what if we change it to something irrational? So take x double prime is minus 2x and y double prime is minus 3y. Then square root of 2/3 becomes irrational. And at first sight, it looks okay. But if you let t run quite a while, then it turns out you get this figure. And if you let t get even larger, then in fact, it fills up the square. I mean, it's kind of cool because even though before the solutions were periodic, if you change the ratio of frequencies to become irrational, you get one of the first examples of a chaotic ODE. And in fact, I want to just give you two more examples of a chaotic ODE, because once upon a time, there was this German guy called Lorenz, and he tried to predict the weather. So he had the ODE x prime is minus 10x plus 10y, y prime is 28x minus y minus yz, so a nonlinear term, and z prime is xy minus 1/3 z. And once again, that was used to predict the weather. Well, tough luck, Lorenz didn't predict the weather, but he predicted chaos, because this is one of the first systems that is chaotic. Because the solution looks like a horseshoe like that. And what's crazy about this is the solution can never make up its mind. Because here's a nice animation of it. You see, so the solution is a marble that just spins back and forth between those two curves. And because it can never make up its mind like that, that's what we call a chaotic system. Now, that's one thing I wanted to mention. Another thing, if I can sort of get out of this, is something I did actually as an undergrad project, because I was very interested in those chaotic ODEs. And that's what's called a homoclinic orbit. And kind of the premise is simple. Suppose you have an ODE such that there's one curve going into an origin and another curve going out. Kind of like our case where one eigenvalue was positive and one was negative. Moreover, suppose those curves intersect again into a point H called a homoclinic. So what's interesting, in the origin, one curve is going out, in the other one out. For the homoclinic point, that same curve is going in, the other one is going out. Kind of like how the heart works. Then it turns out, if you complete the picture, you get something as follows. Wow. I mean, look how crazy that looks. And in fact, it turns out, if you just start with the origin and one homoclinic point, you end up getting this quite chaotic system. And in fact, what's cool is every intersection here is a homoclinic point. So if you start with 2 or 3 of them, you actually get an infinite amount of homoclinic points. So in this case, the system is again chaotic. So I hope that opened up your thirst for ODEs. And really, this is such a beautiful subject. And I hope you will study more of that, because you can get more cool and crazy pictures like that. Thank you.